Okay, next talk is Alexey Ustinov on the periodicity of Somos sequences. Thank you, please.
Thank you for inviting me here. I'm very glad to be here. I'm working in number theory, so algebraic topology is not my subject. And that's why I'm very grateful to Victor Buchstaber, who introduced me to the theory of formal groups. From time to time, I'm getting from him different interesting information about connections of algebraic topology and number theory. And today I'm going to talk about one topic which probably have some connections. And let me start with some basic definitions. I'm going to talk about Somos sequences. The simplest example is here on the screen. What is Somos 4 sequence? The Somos 4, this parenthesis means that we deal with the simplest possible sequence. It starts with 4 units, and it satisfies the following recurrent relation of order 4. And this relation is quadratic. And surprisingly, all elements of this sequence are integers. It's not obvious because every time when we calculate another element of this sequence, we have to divide the right-hand side by s(n minus 2. And s(n minus 2 is some big number, and it's not obvious why the right-hand side is divisible. Here you see the first 80 elements of Somos 4 sequence. You see how fast does it grow. The right border of this triangle looks like parabola. So roughly speaking, this sequence grows like exponent of n squared. Originally, this story begins with Somos 6 sequence. I think that Michael Somos, who introduced these sequences, he was able to prove that Somos 4 and Somos 5 are integer sequences, but next one, Somos 6, was surprise for him. He considered the sequence which is defined in the same way. It starts with 6 units, and it satisfies the similar quadratic recurrent relation. And he posed the following problem in Crux Mathematicorum. Consider this sequence. Computer calculations show that first 100 elements are integers, and he conjectured that all elements of this sequence are integers. And this star means he was not able to solve this problem himself. And in the next year, the integrality of Somos 4, Somos 5, Somos 6 were proved by different mathematicians, but all these proofs were computer-based proofs. And David Gale, who wrote an expository paper about Somos sequences, he wrote that rather than eliminating the phenomenon, these proofs make it more mysterious. And these proofs remind him the proof of the 4-color theorem. The next Somos sequence is Somos 8, and this sequence has no properties at all. And if we try to calculate first elements of this sequence, we will see that they're not integers. And it's natural to divide all possible Somos sequences into 2 classes. First class consists of very good sequences like Somos 4, Somos 5, and another class consists of some kind of wild sequences with no properties at all. The Somos 8 sequence is the first example from this class. The general definition you see here for k greater or equal to 4, general Somos k sequence is defined by the following quadratic relation of order k. Here, alpha arbitrary constants, complex from complex plane, and we have to take k initial values in order to define all elements of this sequence. For example, this is the usual definition of general Somos 4 sequence, no parentheses here. It means that all initial conditions can be arbitrary complex numbers. Alpha and beta are also arbitrary, and also the similar definition for general Somos 6 sequence you see here. The situation became more clear then Fomin and Levinsky developed the theory of cluster algebra. And one of the corollaries of their theory was the integrality of Somos K sequences when K is equal to 4, 5, 6, or 7. We were able to prove more general result. They proved that all terms in these sequences are Laurent polynomials. It means they are polynomials in S1, Sk, and inversed. So it means that, in other words, that it means that any element of this sequence, it's a rational function of coefficients alpha and initial conditions such that the polynomial which stands in denominator is actually monomial. In particular, this theorem from this theorem directly follows that if all initial conditions are units, then elements of this sequence are integers. And this theorem is not a final step. Now we know more strong criteria for the integrality of such sequences, but it's not the main goal of this talk. Probably the more natural way to look at these sequences is to look at them from the theory of algebraic curves. For example, when we deal with Somos 4 sequences, then we know the general result. This result was proved by Catherine Swart and Andy Hone. They proved that the general term in this sequence can be expressed in terms of the Strauss sigma function. Here we have arbitrary constants, A, B. We have some curve defined by plane lattice gamma, and here N2 complex points, Z0 and Z. And Sn, you see the general formula here. If we want to define Somos sequence, we have to know 6 parameters, 2 coefficients, alpha, beta, and 4 initial conditions. And here the same, we have 2 constant alpha, beta, we have 2 constant Z0 and Z, and we have 2 vectors which define our lattice. So more roughly speaking, when we have this formula, it means that this formula is general formula because the number of free parameters is the same as the number of free parameters which we need to define Somos sequence. And the last result, which is known here, the last sequence for which we know the general formula is Somos 6. Fedorov and Hone recently proved the general formula for the elements of this sequence, and they were expressed in terms of Kleinian sigma function associated with some genus 2 algebraic curve, hyperelliptic curve. And here Z and Z0 are some points on Jacobian of this curve. Let me go back to these 2 classes. Which sequences are good? It's natural to define the following class of Somos sequences, which are known as finite rank sequences. What it means that some sequence has a finite rank. We take our sequence Sn and we define 2 infinite matrices. The entries of these matrices are following product. First matrix consists of products Sm plus n, Sm minus n, and here indexes have the same parity, and we also need another matrix M1 where the indices have different parity, and both these matrices, they have to have finite rank. This condition is very strong, and we can say that sequence has a finite rank if some algebraic structure is hidden behind the sequence. In some sense, this sequence has to satisfy some addition formula. Another definition, equivalent definition of finite rank sequence, you see here. The sequence has a finite rank R if there is some finite k such this product for any m and n, the product s m plus n, s m minus n can be expressed as a finite sum of such summands where variables m and n are separated. In some sense, this parameter R, the rank of the sequence, it describes how complicated the sequence is. Many simple sequences are the sequences of finite rank. For the simplest one is just geometric progression. This is the only sequence which has rank 1. We see that Sm plus 1, Sm minus 1, just the product of two functions. One of them is a constant. Another example, just integer numbers. Then Sn is equal to n, and it's also easy to see that this sequence is a sequence of rank 2. Another simple examples are sine function, or any polynomial has a finite rank. Polynomial n to the k has a rank 2k. And another simple examples are Fibonacci numbers, because we can write down following formula for the products fm plus 1, fm plus n, fm minus n, and for this product. And all these examples are special cases of example 6. The sequence defined as values of Weierstrass sigma function taken along some arithmetic progression also has rank 2, because we have following addition formula for the Weierstrass sigma function, which involves also Weierstrass p function. And almost the same is example the Jacobi theta functions. They also have rank 2 because we know that they satisfy following addition formula. This formula is written for theta 1, but also it's possible to write down similar formulae for any Jacobi theta functions. And probably the most general example here is Riemann theta function, because which you see here, you already have seen the definition of theta function in the talk of Alexander Veselov. They also here z belongs to c to the j. This function corresponds to some Riemann manifold of rank of genus G. Tau is positive definite. The imaginary part of tau, matrix tau, must be positive definite. And this function has rank 2 to the power G. So from general formula for Somos for sequence follows that this sequence has rank 2. From the general formula for Somos 6 sequence follows that Somos 6 sequence has rank 4. And it's natural to consider the general sequences which have a finite rank. What can we say about such sequences? What does it mean? In other words, if we take a sequence of rank 2, for example, we can take Somos 4, we can write down a lot of different formulae for these sequences. If you know that our matrix has rank 2, then we can take arbitrary submatrix 3 by 3, and determinant of this matrix will be equal to 0. And we can take arbitrary parameters m and n here, and they give us a lot of different relations for such sequence. Ma, probably he proved also, or conjectured this formula, and he called it magic determinant formula. What what it gives to us. It gives us, in particular, formulae which allows to calculate elements of this sequence using not very many algebraic manipulation. We know that we can calculate points on the elliptic curve using Dublin formula. We need only logarithmic number of steps in order to calculate coordinates of some points on the elliptic curve, and we can do the same using magic determinant formula. For example, we can take parameters n01, n01 here, and we can look at this formula in the following way. We can calculate, we can find S to n when we know elements of this sequence with numbers n, n+1, n-1, or something similar. And this allows to construct different cryptographic protocols similar to protocols built on elliptic curves. Here you see the general scheme. This is very similar to the usual Diffie-Hellman key exchange protocol, but this scheme is realized, constructed on this Somos 4 sequence. And it's important that if you have a sequence of finite rank, then they can do the same. We can construct formulae which allows to find elements in these sequences very fast. So instead of elliptic curve, it's possible to construct cryptographic protocols on hyperelliptic curves. What is written here? This is more or less general scheme. P is some prime number. Alice chooses random number capital A from this segment. Bob does the same. He chooses random number B, and Alice calculates following 4 elements in Somos sequence. It's possible to do it fast. Bob calculates similar numbers, and they exchange these quadruples between each other. And Alice, once he knows its secret A, and knowing the numbers taken from Bob, she's able to find SBA, and Bob can do the same, so they get secret number, secret key, and they can apply the secret key in order to exchange some secure information. So this protocol requires only finite rank sequence. That's why they can have different cryptographic applications. As I understand, we can say that such sequences in some sense integrable, and we can look at these sequences from different points of view. First property, which allows us to say that such sequence is good in some sense, is Laurent phenomenon. Second one is positivity. Positivity here means positivity in terms of theory of cluster algebra. These Laurent polynomials, they have additional properties. Denominator is monomial, but we know that numerator in all known examples are polynomial with positive coefficients. Generally speaking, it's known as a positivity conjecture. For Somos sequences, it's possible to prove that polynomials in numerator have positive coefficients because all these coefficients have some combinatorial interpretation. They count something. Another side of this integrability is reasonable topicalization. I will say a few words about topicalization later. And another side is periodicity. So probably all these properties are more or less equivalent. So it is interesting to find ways to connect them with each other. And probably the most strong of them is a general formula in terms of theta function, because we know that theta function satisfies some addition theorem. So all sequences constructed by means of theta functions have finite rank, but we cannot say opposite. It's not known whether all finite rank sequences can be expressed in terms of Riemann theta functions. And there is a good set of examples. They are known as Gale-Robinson sequences. They constructed in the following way. We can choose positive integers R, P, and Q, such that their sum is equal to some n, and we can write down recurrence of order n. The right-hand side has only 3 summands. It is known that elements of this sequence, they are Laurent polynomials. It was proved by means of cluster algebra. And probably these sequences have finite rank, but it's not known, it's not proved. But computer experiments, they allow us to say that it is true. What is topicalization and why it is natural? We can consider not a sequence consisting of numbers, but polynomial sequences. It's possible to prove the following statement. If we take a Somos 4 sequence where initial conditions are independent variable, S0, S1, S2, S3, and if we take coefficients alpha, beta here divisible by these formal variables, then general term in this sequence is polynomial. In particular, this theorem implies that if we start with units, then all numbers in this sequence are integers. And it's possible to prove the same statement for Somos 5, Somos 6, and Somos 7 sequences. And when we have polynomials, then we can make a topicalization. But before topicalization, why these sequences can be useful, can be important? One particular example of polynomial Somos 4 sequence is a sequence of division polynomials. These division polynomials are usual tools which used in order to prove some properties of elliptic curves. The similar polynomials are known for higher genus curves, and they are also Somos polynomial sequences. So it's not something very artificial. What is topicalization? Let me remind you the main steps here. The main object here is tropical semiring. It consists of real numbers with infinity, and we have 2 operations, tropical addition and tropical multiplication, which are, first one is maximum, and second one is just addition. And we can take any mathematical formula without subtraction and can make the following procedure. We can replace plus by tropical addition, we can replace multiplication by tropical multiplication, and in some cases, this operation is reasonable. For example, if we have polynomials with non-negative coefficients, when we add 2 polynomials, then degree of the result is maximum of degree P and Q. And when we multiply 2 polynomials, then the degree of the resulting polynomial is sum of degree P and Q. So if we have a polynomial sequence when with positive coefficients, then topicalization is a reasonable operation, and we keep, as usually in tropical world, this topicalization keeps some information. For example, if we take a sequence of polynomials, then after topicalization, we can look only on the degrees of these polynomials. Another information is lost, but what we get in tropical world, everything is more simple because everything is piecewise linear. And Somos sequences is an example of is a nice example. The tropicalization gives some useful information. So here you see the usual definition of Somos for sequence. After tropicalization, we have to replace multiplication by addition. Here plus is replaced by minimum. And we have following recurrent relation for the D, where we can say that D is the degree of S, dn is degree of Sn with respect to some of the variables. Say, this degree of this polynomial as a polynomial of S naught. And if we take coefficients alpha and beta as in theorem mentioned before, then the degrees of this alpha and beta are equal to 1 because alpha is divisible by S naught in the first degree. So for the degrees of Somos polynomials, we have following recurrence. And everything is correct because Somos polynomials, they satisfy positivity conjecture. We know that all coefficients are positive. They count something reasonable. And it's more convenient to use another variables. We can take second difference of dn sequence, let it be an. And in terms of these new variables, an, instead of recurrent relation of order 4, we will get recurrent relation of order 2. And if we try to draw points with coordinates an minus 1, an on the plane, then it's easy to see that we will get some billiard trajectory in the rectangular region. So in real or complex case, we have points jumping over elliptic curve, and after the tropicalization, we get billiard trajectory in some rectangle. And probably it's not checked so far. Probably the same is true for more general Somos sequences. And the last phase of integrability is periodicity. Why periodicity is not obvious here? Again, we can take the most simple example, Somos 4 sequence. It starts with 4 units, it satisfies the following recurrent relation. And why periodicity is not obvious? Because if we take congruence instead of this equation, then this congruence doesn't allow us to find all elements of this sequence modulo M, because it's possible that some element is congruent to the 0 modulo M. And that's why it's not possible to divide left-hand side by Sn minus 1, Sn minus 2, because it's 0. So that is why periodicity is not obvious, and we need something additional in order to prove it. First proof of periodicity was done by Robinson. He proved periodicity of Somos 4 and Somos 5 sequences. And his proof was based on Laurent property and also requires some additional, there were some additional requirements on the elements of these sequences. He proved that if it's possible to choose initial conditions such that they are prime to a given module M, and if this set of numbers repeated somewhere, then indeed this sequence is periodic. The set of possible reminders is finite, so somewhere this sequence of reminders will occur again. So if we have Laurent property and if we have this additional property of coprimality, it's easy to see that this sequence indeed will be periodic. We know that polynomial standing in the denominator is monomial. It contains only some powers of these initial conditions. And if we know that all these numbers are coprime to m, it's not necessary to divide by 0. It means that indeed we are able to calculate elements of this sequence using not recurrent relation, but using the formulae for the terms which expressed in terms of rational functions as Laurent polynomials. But his method doesn't allow to prove periodicity of Somos sequences of higher order. For example, then k is 6 or 7, it's impossible to prove this statement. But the same magic determinant property allows to prove it for arbitrary finite rank sequence, and how we can do it. Once we know that sequence has a finite rank, then we can write down a lot of recurrent relation for the same sequence. We can choose 3 by 3 matrix, and here is arbitrary, and we can take kth column of our infinite matrix. We know that this matrix has rank 2 for Somos 4 sequence. It means that the following determinant is equal to 0, and that's why the same sequence, which is Somos 4, must be Somos k sequence for any even k. We know that for some alpha and beta, we have the following relation. So we have infinitely many recurrent relations for the given sequence of finite rank. And we can do the same for the odd k. We can choose submatrix 3 by 3 from M1 matrix, where indices have different parity. So in particular, if we take Somos 4 sequence, it will be also a Somos 5 sequence. And here you see the recurrent relation of order 5. Coefficients here is -1 and 5. And if we have different recurrent relations, then we are able to prove periodicity. How we can do it? For example, if we have a usual Somos 4 sequence, we can take both these recurrences, and first recurrence walk if Sn-2 is coprime to P. Second one walks if Sn-3 is coprime to P. But it's easy to see that from the definition of Somos sequence follows that two consecutive elements of this sequence can't be divisible by P simultaneously. So at least one of these congruences will work. At least one of these congruences allows us to find next element in this sequence when we know previous ones. And the same idea work for arbitrary finite rank sequence, because if the sequence has finite rank, then we can choose arbitrary submatrix A+1 times A+1. Determinant is equal to 0. So it means that we can write down as many recurrences as we want. And the only problem is to prove that the sequence of finite rank cannot have arbitrary long sequences of 0 modulo some prime P. But it's also not difficult to find in our matrix if you know that we have arbitrary long numbers of zeros in our sequence, when we can find appropriate submatrix in our infinite matrix, which is upper triangular and diagonal elements are not congruent to 0 modulo P. So the rest parts of this proof are some technical steps. So I think that Somos sequences are a very nice object, and I know that Viktor Matveyevich wrote some papers where he developed the theory of Kleinian sigma functions. That's why I think that the sequences can have some application also in topology. Thank you.
Any questions, comments? Please.
My question is about Somos for sequences. Main theorem about Somos for sequences you have nth element of sequence is a polynomial. Maybe if we start with rational number, could it be that at some moment the sequences will be integer? If we start not from 1, 1, 1, for example, some rational numbers.
We can start with integer numbers because we can multiply all the elements of Somos sequence by any number. This formula for the elements of Somos sequence is if you multiply all elements by any geometric progression, the new sequence will satisfy the same recurrence. So if we start with rational numbers, we can multiply them by least common multiple of all denominators, and we will get almost the same sequence, but starting with integer numbers.
Oh yes, thank you.
All the equations are homogeneous.
Yes.
Please.
Is the genus phi sigma function connected to this wild Somos 8 sequence?
No, we have additional theorem for Kleinian sigma function, and it means that we deal with the sequence of finite trunk. All these wild sequences, they have infinite trunk, and probably they have no properties at all. Once we have a sequence of finite trunk, then it is nice.
So the sigma function has addition theorem.
Yes,
so
that is why this sequence has finite rank 4, because we are able to write down explicitly this additional theorem.
Any questions?
Losha, is there any interesting theory for non-quadratic recurrences, say, of higher degree?
There are some interesting sequences with higher degree congruences, recurrent relations, but I don't remember exactly who they were. Probably they arise from combinatorics, from perfect matchings, because all this theory is also connected with perfect matchings of some graphs, and the coefficients in these sequences, they count some matchings. And I don't remember exactly, but probably high order recurrences are also arise in this context.
Thank you.
Else questions and comments, please.
Дорогой Алексей, большое спасибо за доклад. Значит, I should like mention such very important case. In the talk of Alexey, we met addition theorem for sigma function and addition theorem for theta function. But there are famous Riemann-Schrodke problem. What is it? Consider the abelian manifolds. In abelian manifolds, you can construct theta function and obtain addition theorem. Problem. Can we recognize using theta function, we work on any abelian variety or on the Jacobians. And Sergei Petrovich Novikov предложил to solve this problem using the Kadamtsov-Petviashvili equation. But in papers Buchstaber and Krechever, we suppose other approach, exactly using the addition theorem. And what I might ask, did you know what our functional equation? What we mentioned. Let us consider addition theorem for theta function. In the left, you have function from x plus y, x minus y, but on the right, you have function, it's a sum. The product function depends only on x, only on y, addition theorem. But arise invariant, how many summand here? And we introduce, exactly as in your formula, the number of k, the sum from 1 to k, as complexity addition theorem, and suggest psi hypothesis. If it is theta function on Jacobian, the sum must no more than G. The G is the genus of curve, but in general case, it's 2 integrate G. So, and after some times, Sam Grushevsky proved our theorem, and the problem of Riemann-Schotke was solved using what approach Buchstaber-Krechever. But let me remind you, theta function you can construct for abelian manifolds. But if you should like to obtain sigma function, no. It was a very famous problem of Felix Klein. What is mean? What is mean sigma function? It turns out if you have Jacobian hyperelliptic curve, rise, as we now know, sigma function of hyperelliptic curve. With Leikin introduced notion NS curve. So the problem such, not you have theta function for any abelian variety, but you cannot construct sigma function. You must find additional condition for the abelian variety, which give to you the possibility to construct sigma function. So, but in your construction, we are using sigma function and theta function. It will be very interesting using the high dimensional sigma function. You mentioned the result about the genus 2. But the first non-trivial example, as you know, it's genus 3. Because in genus 2, any abelian variety, it is Jacobian. The first example arises genus 3. So, and we have addition theorem for sigma function, sigma 3. And my suggestion, could you consider the case genus 3 from such point of view? You can using the theta function genus 3, you can using the sigma function genus 3. Certainly arise difference. And maybe difference you can realize using what this ideas from the Somos. So certainly it is what your talk give to me new ideas and new problems. And I suggest consider this area from point of view what new result in the set of sigma in theta functions. Thank you.
Thank you. Very nice comment. It's necessary, yes, to look more carefully at your articles.
Okay, else questions, comments? Okay, let's thank speaker again. And now go to lunch.